Ladies and gentlemen, please welcome back to the stage Manju Hegde and Mr. John Taylor.
Good morning. Welcome to the third and final day of Fusion 11. It's very gratifying to see so many of you here for our closing keynote, which will begin in just a moment. It's especially gratifying considering all the fun we had last night at the Unsummit happy hour cocktail reception. It was just really very cool. You guys have seen a lot of demonstrations on stage, a lot of things that we prepared for you. But last night, people were breaking out their laptops, showing the interesting things they were doing in code, new innovations, the next big thing. And that was just a really fantastic experience. So thank you for burning the candle at both ends with us last night and now back again this morning to finish strong. Because in life, in business, in technology, in sports, it's always important to finish strong, right, Manju?
Yeah. And let me tell you a little bit about our next talk. Now, as you know, graphics is one of our core technologies. In fact, we often use it to differentiate our products. Now, this week, we've talked a lot about the APUs. The first keynote from Phil Rogers was a lot about the APU and the APU roadmap. And frankly, it was hard not to do that because it was also the week, as it turned out, when we were launching the era of the Fusion APUs. And what we're doing with the APUs, if you look at it, graphics is one of the core differentiating technologies there. We want to make the GPU very valuable to mainstream experiences. And then we want to create a hunger by mainstream users for those graphics experiences so that when you add a second discrete GPU, the two add up and give you dual graphics. So people always say, won't the APU market now hurt and kill your GPU market? And that seems very counterintuitive to me. The answer, of course, is a resounding no. Because when you go to a restaurant, don't you eat appetizers? And does that reduce your hunger for the main course, or does it increase? I know I eat a lot of appetizers, and I then consume a lot of main courses. So now let me tell you a little bit about Eric Demers, our next speaker, who's going to tell you about that core GPU technology. Eric is a veteran of the graphics industry. I think he won't admit how many years he's been there, but I know he was in ArtX, which was acquired by ATI and subsequently acquired by AMD. At AMD, as CTO, is responsible for the entire graphics roadmap, which includes discrete GPUs as well as APUs. There is nothing in graphics that he doesn't know a lot about, and a lot in graphics that he knows everything about. So in order to serve up the main course, let me invite Eric Demers on stage.
Actually, before we bring Eric out, just very quickly, so let's take advantage of our giant display yet again. And take a look at what Eric and his fellow hardware and software technologists at AMD, but more importantly, with you, the developers, what we've achieved to this point. So let's roll that video, and then we'll be joined by Eric. Thanks.
Okay.
Ladies and gentlemen, Mr. Eric Demers.
Thank you very much. I hope you enjoyed my video. That final statement and that's just the beginning, is actually sort of a bold statement. The vision I had behind that video was really to look at all the software you guys, all the developers have created, and look at the GPU platforms we've put together over the last 15 years. And 15 years was an appropriate amount of time because I defined a GPU as a sort of consumer device with 3D graphics integrated that, that really spawns that industry and really started for us, say, with the Rage products in 1995 and has grown since then. Look over those last 15 years and show that evolution in a really visceral way. And then to end that with a bullet that says, and that was just the beginning, that's pretty bold. This was a great introduction to what I'm going to talk today, and I'm hoping that that statement, you'll agree at the end, sort of makes sense for what we're planning. And you agree with it and you walk out of here going, wow, AMD has that direction. So I actually have two parts to my presentations. The first part is really going to look at that 15 years. And what I really want is not just to show pretty pictures, and I definitely will do that. It's not just about calculating pi. But I will also show why we've gotten here and how we've gotten here and the logic behind it. A lot of people go, wow, you're doing stuff in a certain way. There's a reason and there's a rhyme for that. And then that'll set the stage for the second part, which is where do we go next? So early eras, like I said, Rage 1995, that's the start for AMD, and back then it was ATI GPUs. So I look at the first era, and we've defined these to be very AMD or ATI specific eras. That's okay. This first era was all about fixed function. It was taking the first 3D capable GPUs, adding a simple model that was available in the D3D and OpenGL APIs of the late 90s, and implementing that in hardware and accelerating the heck out of it, right? Going from a CPU-based to 1,000-fold increase in performance with this fixed function. But it was all fixed function. That programming model was simple. You could turn features on and off, but it was all fixed function. You couldn't go change, radically alter how things were done. That's fine. Here's our, oh, sorry, went a little faster. Here are some images. So Creative Assembly, Shogun, Total War, definitely has 3D. Strategic game using 3D enhances it. Feels like you're playing a board game. It's a great experience. It was quite an experience when it came out. Here's Radeon's Arc. Came out with our Radeon 7000 in 2000. Again, the same simple programming model, but we pushed it to its limit. We did environment mapping. We did a lot of cool features that said, gee whiz, this is 3D. Fun fact number one. I have at least two fun facts throughout this presentation. That is not the Ruby character. I did some research on that, and I found my team, no, nothing to do with Ruby. Yeah, it's a woman, and she's got hair. That's about as far as it goes. Having said that, I found so many articles that were saying, yes, this is the start of it. No, it wasn't. Having said that, I can't imagine there wasn't a certain inspiration for later models. And from Codemasters, the Colin McRae series. That was a really fun, visceral experience back then. I do actually remember playing that. Now, by today's standards, quite primitive graphics, but still a fun experience. I don't want to scare anybody with the math. It's okay. But I wanted to illustrate what that modeling was back then. The first part of this chart really shows object space transformation. You have your objects in 3D space, and you want to get them on your screen. So you do a little bit of math, and you get it there. Second part is about what color should those pixels be. It's a very simple lighting model. It looks more complicated than it really is. It takes an ambient component, a diffuse, and a specular, and simulates some sort of version of reality. If you actually look and study some of that, it's really all based about linear algebra, and in particular, 4-component dot products. And if we boil that down, that's 4 multiply accumulate units. And then there's scalar elements to that. There's divides, there's attenuation, and power functions. So you end up with some pretty basic math to do all of this. Linear algebra implemented in a dot product, and scalar to finish off the work. 4 multiply accumulates, and a scalar coprocessor to go with that. There's a certain trend that we're going to start seeing emerge from that. This implements this model in a very straightforward way. Obviously, back then, the precision wasn't anything we talked about, in fact, but it was mostly 32 bits on the geometry side and somewhere in the fixed point 8 to 12 bits on the color side. Things evolved. Performance from 95 to 2002 kept on increasing. At the same time, the demand for higher quality was there. Late 2001, instead of looking at what we could really do with it. But it was fundamentally changing things. Applications now come in and go, well, I don't necessarily need to use that old model. I could do something completely different. Right, not completely different, but somewhat different, and start controlling both first on the vertex side and later on the pixel side what you can do. Obviously here R300 was a great example of that. Our focus continued to be exclusively graphics. Graphics was paying the bills. We were driving this with shaders that had floating point and integer capabilities. That was the basics of the simple programs. Here, medieval Total Wars, again by Creative Assembly, one notch up. Started doing things, more subtle shadows, more realistic 3D effects, as well as more complex textures. Dirt, the first Dirt from Codemasters. Huge step. Part of the quality difference is obviously the images that we have back then, but the reality is that it was it was a game that I still clearly remember going, wow, that looks amazing, and it's running fast. And then in 2004, we launched the Ruby Double Cross demo. To me, this is borderline cinema kind of quality. Now, I'm not talking real cinema, I'm talking animation style cinema. But wow, the skin shaders we had on that, the complex vertex shaders, it was really at the time, and I hope some of you remember, it was really at the time an amazing experience to see that. And it was really pushing the limits of all the data that we had for these models. Looking at the pixel pipeline there, it was, again, an evolutionary step, but it was a significant evolutionary step. We now had 2 pixel shading stages, the vertex shader and the pixel shader. But here's the funny part. The math inside was still pretty much the same. We had 8 copies of a dot product and a scalar in the vertex shaders, and we had more of a simpler, just straight dot product on the pixel shader. Again, precision wasn't that much of an issue. We were mostly front end on the 32-bit, not IEEE. And in the back end, we actually did a hybrid of 24-bit until we eventually converged to 32 bits to resolve some issue. It wasn't IEEE compliant, but it was programmable and it was floating point. 2007 was what I consider the third and last era here, the start of that. During this era, I'll be honest with you, graphics has still been our king, right? It's still been what we drive. But during this era, things have evolved. It required us to take these multi-shader designs, especially with DX10 coming out. We actually had creation of new kinds of shaders. And instead of doing all of that, we folded it all into one central location. And then we imposed the requirements of all the different shaders. And then we built up on that, on top of that. And over this period, we actually introduced IEEE. We introduced double precision. But fundamentally, we still wanted to be good at graphics. And we had a core of a dot. And we had a core of a scalar working together. This made a lot of sense. In 2004, Stanford Brook started showing off generalized C programs compiled in vector format to run on GPU. Now, it wasn't easy because they were compiling it to a GL or compiling it to D3D and getting it to run as a graphics application. But clearly, they were starting GPU compute. And the third era is really where GPU compute really started up and really expanded. At first, we we had these proprietary solutions like Cal and Brook, and since 2009, it's really evolved to industry open standards, either through direct compute or through OpenCL. And since then, really in the last 2 years, it's really exploded. But at the same time, we also saw applications such as workstation-style application. I still remember workstation from the 90s running on machines that I couldn't afford, but I was working on, and it was cool to see those things. But throughout 2000, especially after the acquisition of FireGL on our side, we started working with a bunch of different partners. And here we have from Dassault Systems, CATIA running in 2009, running an Infinity, running a very complex high polygon model of a really cool looking motorcycle, and with really complex lighting, taking advantage of that core, not from a compute standpoint, but definitely pushing the envelope of graphics. Dirt 2, another step ahead, and we launched that with, roughly at the same time as our HD 5000 series. It really pushed the envelope. It was the first game that I would really say those cutscenes at the beginning of the game and the in-game feel were pretty much the same. And from Autodesk, architectural navigation through a world using 3ds Max, where not only lighting and shadows are computed, but even material properties. And you see the menu there for the material properties are being simulated and run through using shaders and delivering a rather visceral walkthrough of a potential future design that you're doing, a future building that you're doing. So if we look at what was inside that unified shader core, we had that dot product and scalar. Pretty straightforward still. I think it's becoming a theme at this point, in case you hadn't noticed. VLIW5 was our way of programming it, because it was really straightforward and it mapped to the graphics, and it was relatively easy in the sense that, wow, if we have all this shader code, we can just use a compiler and bang, map it directly to that hardware, and it works well. We were able to achieve on graphics, typically I think Mike Houston talked about 3.8 instructions on a VLIW5 today. And over time, especially earlier at the beginning of 2007, 2008, with a lot of graphic content, it was even higher than that. It's very high utilized, very optimized for graphics, and it does that same thing. Now, you could argue, well, hasn't the pipeline improved? Yes. People are doing more radical things. They're doing deferred lighting. They're doing a bunch of stuff. But a lot of those core concepts from the late 90s are still alive and well. You still have to take object space and move it to the screen. You still have compute pixel shaders, and now maybe you do it at the per pixel level and you're doing it as Phong, but there's still the same components there, and this architecture works well. And in fact, this architecture, when we start using it for generalized compute, works okay, but it leverages the graphics. Texture cache is the primary input. It's a one-way street on this kind of architecture. It's massive amounts of bandwidth organized for texture reads, getting all of that data in. Now we use it for compute reads. And then we stream out that output on compute out. So we added that just for compute. Graphics, even in this era, is still our primary focus. I can't help but say the third generation keeps on evolving, and it's worth talking about what's happened, particularly in the last 12 to 18 months. Graphics still is key. Still go to OEMs and they ask you, what is your graphics performance? A lot of folks are still focused on that, and that's not going to change for us. But we are making significant optimizations for compute. We are looking at things differently. We're also enabling high-performance compute. We're enabling VDI solutions. We're enabling a lot of things that aren't what we would call classic graphics. Here's an example of where compute meets graphics. This is our HK2207 demo that we launched initially in October, but then we had the final version in January. And this demo uses GPU to do all the particle physics. It uses deferred lighting with G buffers. It does post-processing as a compute operation. It does very complex operation. And what is compute and what is graphics is blurred. And we pick and choose the elements that we want to end up with the solution, the visual solution that we need. Here, Dirt 3 a few weeks ago. Very cool game. Again, pushes the envelope. contact shadows, even more direct compute to get high quality water effects going, wind and cloth physics. It's fantastic. A lot of fun as well, and it runs really fast, and it's quite a visceral experience. If you guys were there on Tuesday night, we had an Eyefinity set up with DDD running that in stereoscopic, and you got an eyeful. Oh, I assume a lot of you may have seen already what it looks like, but it's pretty cool from Codemaster still. EXA, this is a BMW motorcycle. Yeah, I thought it looked cool, so we had to find out. And it's doing airflow simulation. So here the GPU is computing the airflow simulation and showing you the thermal distribution and the energy being shown, but also renders the results. That's a common trend in a lot of high-performance computing. You compute something heavy and then you want to show it. Because just like Nigel said on Tuesday, visual sense is still key. And Optus, they were in the dining area 2 days ago. I haven't seen if they were there yesterday or they'll be there today. But they're doing ray tracing. They're doing ray tracing on OpenCL on our GPUs. They're famous for doing cars and the insides of cars and simulating what they're going to look like in a real-world circumstance, reflections on the windshields when you're driving, so you can really optimize the design. But all of that needs to be ray traced, and they do a fantastic job, and all of that is running on the GPU. And in fact, this is a trend that we see happening right now, more and more, particularly, like I said, over the last year. We've started shipping in server systems, so virtual desktoping is big for the cloud. But the capabilities of the GPUs are being used. You guys, I hope, have gone to a lot of our technical presentation. I went to a few of them, not as many as I would have liked, and so many of them were about high-performance computing and molecular docking and all types of very dense computations that we've been able to improve significantly with the use of GPU. And this is only going to continue because the demand for more compute and for parallel compute is only just starting. To deliver a better optimized for compute workload, we made some changes in one of our products for, that we launched in FirePro a couple of weeks ago and in Consumer last year. We actually, for good reasons, changed our VLIW5 approach. Again, VLIW5 optimized for graphics, it's a natural. We went to a VLIW4, and then we made it symmetrical, meaning we balanced out all the features that were in that fifth unit across all of those units, so they become symmetrical. They're all effectively the same. This has a couple of neat properties. One is if you're trying to utilize all those lanes, having less lanes is easier. You can get better utilization. But also being symmetrical means that a compiler that needs to find work to be done has an easier job of scheduling stuff. So efficiency on compute continues to go up. Efficiency on graphics is good, so there's really no real sacrifice there, in part because graphics and compute have become intermingled as well. Obviously, from a hardware standpoint, designing one unit and replicating it, it's not quite fair, by the way, but generally speaking, is like that, is a lot easier. You don't need to verify multiple different elements. You don't need to optimize multiple different elements. You can focus more of your energy on one. If I plot, and that plot is an approximation, interpolation, and extrapolation, all those nice words, of our cores in this third generation, you can see a trend emerging. And it's been a good trend. And in fact, it's been an amazing trend in terms of compute in my book. Our latest product's nearly at 3 teraflops. That's a pretty amazing thing. Those are numbers that people didn't even know that there was a tera. Feels like a few years ago. Maybe hard disks beat us to the punch there, but it's been amazing. And now extrapolating from that curve is, is guesswork a little bit. Maybe not so much for me as others, but fundamentally the curve keeps on increasing to the right. What slope it follows, some of that is our own architectural work, some of that is also process and technology out there, but it's continuing to improve. And it's driven by gigaflops per watt. The power segments of a lot of these products don't increase. In fact, if anything, they're decreasing. So we drive these higher performances by actually improving our performance per watt and then leveraging that and turning into power, into performance. And ISVs, a lot of people here love this, right? You talk about computing and HPC, they all want to have this. You also want to use it for graphics. So it's been a natural that this increase, which is in part due to the nature of parallelism, that you can always add more stuff, not always true on the CPU side, this has attracted them tremendously. And then with the catalyst of OpenCL and direct compute basically setting industry standards, now they're putting their own engineering efforts into the flow. They're putting their engineers to work. When it was proprietary standards, you sort of had to pay them or you had to do the work, in a lot of cases anyway. Now all these companies, and this is not an exhaustive group, you know, we talked yesterday, Corel presented the whole Kronos list, and you know, there's a bunch of game companies in there, Blizzard and EA and so on. This is just some of the new ones that we've added, and it continues to grow at a tremendous rate. Just keep on adding, because they want to take advantage of this performance and use it for themselves for both graphics and for compute. Now, that sets the stage. That's where we are today. That sets the stage. Going forward, with higher and higher performance, we want to make sure that applications can come out and really unlock the potential of the AMD platform. We've seen and learned enough about our architecture that it made sense for us, and we started this, like I said, about 3 years ago, to start working on putting in all the elements that we really need to take this heterogeneous platform and make it an amazing platform for programmers. We need to simplify the programming model. We need to unify the memory. And that's how we came to the Fusion system architecture. And that's the second part of this talk. It's all about what we need to do going forward. So I creatively acquired Phil Rogers' slide from his presentation in the beginning. If you are like me and you looking at this slide, you go, wow, there's a lot of stuff on there. Well, there's some good news. If you look at Alano program that we just launched this week, or Ontario at the beginning of the year, that first column is pretty much done. Can't say we can't improve it, but it's pretty much done. Awesome. Then I look at the second column. Oh, GPU compute C++ support. Oh yeah. User mode scheduling. Oh yeah. Oh, that's good. Oh, third column. Unified address space, CPU, GPU. Yeah. Oh, coherency. Yeah, that's nice. GPU graphic preemption. Wow. Those are amazing features, and it makes sense to implement them in the platform to ease and unlock that potential. But the reality is it's hard to do all of those things. So when we started working on this, we realized, wow, we're going to need either to evolve significantly our current platform or effectively rewrite the GPU core. And rewrite the GPU core we did. So if you attended Mike and Mike's presentation, you should recognize that this is a version of their presentation. The fundamental thing we did for our new shader array in this new architecture is create what we call the compute unit, or CU from now on. The compute unit is sort of the cellular basis for this thing. Just like we've had what we call generally SIMDs on our current designs, now we talk about compute units. This is a new design. Obviously leverages the knowledge we've had from our previous designs, but it is fundamentally a vector core. So if you look at that core up there, the vector unit, that is effectively still a SIMD array, but it's programmed in a per lane basis. There's no more VLIW at all. It's a little more complex than that. It's actually running 4 groups of wavefront on 1/4 of that SIMD every cycle over 4 cycles. But the way to look at it is that it's a vector core where each lane is programmed independently, and there's a single stream coming in and broadcast to all of those things, and you program it in a scalar way. And it operates in a vector mode, and it's a SIMD array underneath. Now, that's cool. And it's supported by a much larger L1 data cache with significant amounts of bandwidth, and I'll have a slide coming up. And supported as well by control systems. So historically, our designs have had what we call hidden fixed function with hidden state. Fixed function that did, for example, program counter advancements and things like that, limited functionality. what we've done is we've created a scalar coprocessor. The scalar coprocessor is a fully observable design, and it's a processor in its own right, and it's responsible for all the common kind of code that will, for example, the branching code and all the common pointer arithmetic. The truth is, the vector could also do that, but the coprocessor, the scalar coprocessor, helps it out and offloads those capabilities. The design is very, very similar to, if you look back on the Cray, one of our partners, the designs of supercomputers that did vector supercomputers of the 80s. This is exactly what it looked like. And I will say that is definitely one of the inspirations we had for this kind of design. Now, this compute unit can work in virtual space, and it will support the x86 addressing virtual space, right? It will support the x86 64-bit virtual address space. But the fact that it's fully observable, the fact that it's fully programmable, and that's really a generalized purpose compute, the fact that you can load the PC from memory or from a register and do all kinds of math, it opens up a huge set of features for us. So those C++ features, virtual functions, recursions, and with x86 dynamic link libraries, all of these things become a native thing that this guy can support. So by designing this new design, we're able to implement at least one of those big blocks in that list of FSA features. But that's not all. Actually, let me put it a different way. This is a question that I've been asked. What do we call this architecture? The reality is this architecture has a lot of different properties. Because there are 4 wavefronts every cycle executing on the vector and scalar units, and these can come from 4 completely different applications or from the same application. It's really sort of a MIMD architecture with a SIMD vector array. Obviously, it has a SIMD vector array. And then there's up to 40 wavefronts living in a CU that any 4 of which can run any cycle. So it's sort of got a SMT properties. So what is it? The reality is it's leveraging all that goodness from all those different architectures. And to put one perfect label on it would not be fair. But it is still fundamentally a parallel processor throughput engine, right? It is still what serves graphics and compute and still has all the same properties that we've come to know and love and leverage. It can still hide memory latency by having tons of data parallel work to do. Just a little note. This unit is, these compute units, if you put many of them, still need to be fed. And we introduced in our Cayman product late last year a prototype feature of having multiple GPUs being able to feed that core. And by multiple GPUs, it's actually multiple inputs to the GPU, multiple separate command streams. Don't think of each of these command streams as one application. No, each command stream can be multiple applications. But they can all have different priorities, and they can reserve compute units for themselves. Here's a perfect example of that. Your GUI, your graphics interface, can be running at one priority level that you can set to high, and you can guarantee some amount of compute units always available for it. But then your big background applications for transcode can be running at a lower priority and fill in the blanks on the compute. You will have a great quality of service. There's no more skipping mouse when you do a big job because the big job is running in a separate queue. Those are some of the capabilities all of our cores going forward are going to have. To back up the compute unit, we need a new memory system. The memory system historically has been a read-only cache. Now it's a read-write cache. It's a generalized cache just like we have in CPUs. Very high bandwidth. Each CPU has 64 bytes of bandwidth to that local L1. If you think of just a CU as an equivalent of a SIMD, which isn't the case, but today we ship with 24 of these, 24 CUs would be 1.5 terabytes of bandwidth to their L1 cache. Pretty good numbers. If we put 100, not saying we're going to put 100 right away, that's a lot more. That's 6 terabytes, assuming we're running about a gigahertz or a little shy of that. Nearly 6 terabytes of bandwidth. It's huge, the potential here. Then we have a full interconnect between these L1s and L2s. The L2s are more physically based. They match your memory. And these L2s act as the backbone and are also where all the coherency happen. So that's what I mean by the physical binding of the L2s. So when the L1s request, they get all their data out of the L2s. When coherency is required between CUs, the coherence, like the release acquire system that we discussed, that's all handled in scoreboarding in the L2s. Everything from a coherency standpoint is handled in the L2s. And then when we talk about GPU and CPU coherency, again, that'll all be handled at the L2 level. It'll be L2 of CPU with L2 of GPU, all working. And I'm talking probe traffic. I'm talking all the usual stuff you come to expect on coherency. It's really extending the SMP system to include GPUs. And on discrete GPUs, we will tunnel that data over PCIe. So discrete GPUs and Fusion APUs will use the same core technology. Now, I talked about x86. What does it really mean? Well, it means that our GPUs have to have address translation caches. Basically, they take virtual addresses and they translate that into physical addresses. We actually already have that in our GPUs, but now they have to be talking x86 language. And then on the CPU side, an OS visible I/O MMU, just like the CPU as an MMU, which handles physical to virtual translation for the CPU, needs to exist. And we have, as part of our plans, both on our discrete CPUs and our APUs to have I/O MMUs going forward in 2012. And these parts, when paired with the proper GPU, will be able to support address translation requests. And when the address isn't translatable, i.e. page fault, the GPU will be happy with that. Well, it won't necessarily be happy, but it will survive that. It will wait till that page is brought in by the operating system and made local, and then bang, it'll keep on running. So these GPUs will be able to deal with page faults and deal with the full x86 virtual address space. And all the goodness that comes from a virtual address space, over subscription and all those things, will be available for a GPU. Obviously, OS support is required for I/O MMU, and just like it is on MMU, so we're working with OSVs. Our plan is to take this that eventually all of these devices, whether CPUs or GPUs, are in the same unified 64-bit address space. So, recap. GPU support of C, C++, and other high-level constructs, like I said, that's coming with the new CU. Virtual address space, I think I just talked about that. It's coming with this new design. Page faults, that comes as a natural being able to support, well, it comes as a requirement to supporting virtual memory. That's coming in this design. Memory coherence, it's going to be handled at the L2 level between CUs and between the CPU and GPU. Because our core is fully observable, its state is not hidden, saving that state off and reloading it certainly makes context switch much, much easier. Now, there still are some fixed function elements in the pipe that we need to work on, but fundamentally this core can support context switch and will support context switch and preemption. Context switch on a page fault or preemption when you need it. And I'm not talking about an APU, I'm not talking about GPU, I'm talking about an IP of a core that's going to be used in all our products going forward. And over the next few years, we're going to be bringing you all of this throughout all of our products that have GPU cores. So what about 3D in this world? Well, I did say 3D and compute are starting to merge, and in my mind, they already have. But we're going to continue to drive forward. Somebody recently asked me about APIs. We are full of ideas for graphics, and we still love APIs, and we believe that developers will continue to use API because they're an easy way to approach. Some will maybe want to go directly to compute. We encourage all of those things. But we're going to keep on working with our partners and through Kronos, our partners Microsoft on DX and Kronos, to continue to expose more and more of the features we have in hardware. So an example that this core will support is because we require OS support to do virtual memory, in a Windows 7, for example, organization, we can't actually do true GPU virtual memory. But what we can do is leverage all of that good hardware and do what we call partially resonant textures, or PRTs. This is the ability to effectively tell an application, look, create textures of any size you want, and then bring in the parts that you need when you want them. Or if a bitmap is not loaded, we'll actually tell you that you requested it and not loaded it. So applications can start managing their memory and mapping what is virtual and what is physical. You've heard of mega textures from some ISVs working on this. This is a subset of what we can do, and we've implemented all of this in hardware. This is a unique capability that's derived off of a virtual memory subsystem on these cores, and we're going to be bringing that to the play. And that will be usable directly in APIs today. And we're going to continue to push DX11 and work with Microsoft to expose more and more features, and there will be new iterations of that. Just like on OpenGL, we will continue to push that side of the equation, as well as espousing the ability to directly program an FSAIL or combining all of those things. And fixed functions, I mean, they're there. I mean, we don't want to get rid of any of the things that are good in our core. So raster ops and Z units are still part of this. They have their own caches. They have their unique capabilities, that is fixed function, and all of these will continue. And in this new architecture that, I think I stole another picture from Mike and Mike, scalable primitive rates, scalable pixels, all of these are native attributes of this architecture we're going to be introducing. And a lot of that is fixed function and unique to graphics, and we're going to continue to support that and continue to drive that forward and continue to put more of those units as the cost and process allow us. And the new read-write cache is going to be usable as a texture cache as well. And in fact, it's going to gain some of the properties that it has. Larger caches, higher throughputs, those are going to benefit texturing as well. And going forward, I really am excited about fusion system architecture and 3D merging, compute and graphics API and hybrids of all those things. It's really cool. Some of our demos like OIT already start mixing that. Where the future is going to lead there is an exciting place for us to be exploring. And in fact, exploring together. I'd like to call ISVs that are interested to work with us on this specifically. It's just an amazing field. So where are we going with all this? What will this platform deliver? In my mind, anyway. So the true virtual memory is exciting. Volumetric textures that can't fit in memory. Massive data sets, massive textures, all of these things are possible. Streaming on demand. No more glitching when you go over the crest of a hill because all these textures are being loaded, because you can start preloading and loading lower levels and fitting that and managing your own memory as an application. Those are all very exciting to me. The simpler and more powerful programming paradigm that we've created here. Basically, you can program in higher-level languages. You can start executing task graphs directly in an APU where you have effectively CPUs and GPUs working together to execute on these task graphs, doing the serial components on CPUs and the parallel components on GPUs. In fact, that really leads you to the next one, which is braided parallelism and nested parallelism. Doing outer loops on the CPU and inner loops on the GPU, or doing task parallel and serial parallels with dependencies. As fusion system architecture, you saw those little drawings and little animations Phil showed. The ability to actually schedule, having a GPU schedule back to itself and schedule to the CPU, those kinds of abilities are amazing on this platform. And this GPU core will do that and will allow graphics to do that. A lot of game engines use task graphs already. This maps naturally to our architecture. Scalable and open. Obviously, this architecture from a single CU all the way to some large number of them is scalable. It's inherently scalable. And so we expect to use it in our lowest power devices all the way through HPC kind of devices. And open. FSAIL for us to be successful and FSA to be successful needs ISV engagement as well as ISV engagement. So we do intend to make all of these be published specs, and we do intend to work with IHVs to get them to adopt some version of this, if not exactly the same. And we're flexible. We can change a few things to adapt to industry needs, but we want to make it an open standard. Emerging general compute can really start taking advantage of this as well. High-density computing is a clear example, putting many of these. This is a more memory and bandwidth-efficient architecture than what we've had in the past. And finally, We talked a little bit about this last night. I can't say this is AMD's vision. It's more of my vision. But I want to be pushing pixels. I want to create realities that you can't tell that you're not looking through a window. And in fact, I'd rather you can't tell that you're not inside my reality. And I think this is another way, another chunk in that vision. And we have so many ideas of more chunks to add to it. But to me, this is all going in the right direction. Finally, to all the developers out there, this is also an invitation. I don't know about you, but I get goosebumps when I look at all the cool stuff that's going on right now. Thank you very much.
Okay.
Hey, John.
Eric, thank you so much.
Sure.
We really appreciate that. We know you took some extra time, some extra care.
I noticed that you noticed.
Important material. So thank you guys very much for your attention. So we do have some time for Q&A for Eric. Same process that we've used previously. The team with the microphones are now in your midst. I know we already have a number of questions, Eric, sparked from the webcast.
Sure.
So we certainly will get to those, but I want to start with here in the room. You have our graphics CTO on stage talking next-gen, massively parallel architectures. I know there's going to be some questions right here. Mic number 1.
Okay. Right here in front of you.
You should be right here.
Okay. 3D graphics in web browsers, 3D graphics from the web. Mm-hmm. You know, we've failed twice with X3D and Vermal. WebGL looks interesting. Bandwidth is going to be a big, big issue to make that work. You know, any thoughts, any ideas, what can you do to compress 3D vector graphics across HTTP?
Great question. I still remember Vermal days, how that was going to happen, and wow, that grounded to a halt very quickly. There's a couple of things that are required. For example, having every potential client out there be incapable of rendering the 3D is an essential element of that. If you're talking about 10% of the market, right away you sort of create a bottleneck that's unsurmountable. With us, for example, shipping amazing capabilities in all of our products going forward from an APU standpoint is a big sign that AMD's waving a flag saying we're going to be pushing this. As well, a lot of the concepts that are being pushed in terms of compression, graphics command streams being pushed down is a highly compressed version of what you're actually going to render. It's an amazing amount of compression. And what can we do to improve that even further? Well, it's going to be about the content. So there are some capabilities, for example, being able to decompress JPEG and decompress standard texture formats that our GPUs are quite good at that. So as that data is streaming, we can actually decompress it and turn it into other forms of compression that can be mapped as, for example, direct texture maps. But just like in DX11, we introduced two new big forms of compressions. We continue also to push that envelope. We want to continue to improve and get down to, say, 1 bit per pixel kind of compression ratios so that we can really improve things and make that bandwidth requirement isn't going to be grandiose. In fact, I would actually say what's likely to happen when it gets to to an acceptable level, the content's going to increase more and more. So I am actually excited about 3D. I haven't seen a huge amount of it so much yet on the web, but I think it will happen this time.
Eric, let's knock out a couple of these from the web that are queued up here. So the question is, what is AMD doing to push double precision performance? Will double precision capability be available on the GPUs of the APUs, or the on-die GPU, and in cheaper mainstream discrete GPUs in the future?
Good question. So since 2006 or 7, I forget now, we've had double precision in some of our corners. This new compute unit actually supports double precision. In fact, it supports it at half rate, 1/4 rate, and 1/16 rate. It doesn't support it at 0 rate, and right now we don't support it at full rate either. So natively in this architecture is the capability to always have double precision, and then you pick and choose, depending on your part, what level you want. Obviously, parts intended for HPC or high performance will be at the higher end of that, but even our lowest APUs will have double precision when they take advantage of a core like this or its brethren.
Terrific. Thanks, Eric. Next question from the webcast. The memory bandwidth for both CPU and GPU is very important. How does the bandwidth increase for upcoming Fusion APUs?
Yeah, that's great. So there's a couple of different technologies out there that we're looking at. Obviously, there's some easy things you can do, widen the interface and run it faster. Those are things where we may do or may not. Widening is actually not a cheap thing. But clearly now Llano will support up to 1866 memory, and that's actually that's almost 3x anything we've done in the past on a CPU, and that's a big statement. You need to power. You need the bandwidth to supply that GPU internally. So as we scale up in performance, we are going to find ways to increase that bandwidth. So we will continue to push that bandwidth rate. We will look at widening, and then over time, there are technologies on the horizon, such as stacked DRAM and potentially other SerDes kind of solutions that we will definitely look at on the APU side as well as on the GPU side to keep on at the same rate as our APUs, as our ALUs are going up, to give the bandwidth that is required.
Thanks, Eric, very much.
Sure.
I'll do one more here from the webcast. Is there a chance to see GPUs with a hypertransport link? And will we see Fusion APUs, AMD Fusion APUs, as a really supercomputer with 4 or 8 channel memory, ECC, and everything we scientists want? I think it could have come from the room here too, but we got a lot of the scientists on the web as well.
So this core also supports, this was actually at Mike and Mike's presentation. It's not an unimportant detail, but this core supports what we call compute ECC. Basically, all internal SRAMs and potentially every internal data path can be covered as part of ECC. So we designed that in there. That doesn't mean every one of our products will have internal ECC available. We will pick and choose based on which products are appropriate for which markets. And it's actually not always what you would think. It's not only high-end HPC can be embedded. There's multiple things. But the capability is there, and it's our choice to use it or not. Certainly, what was the other part of the question?
Oh, it's not up here anymore. There was ECC.
ECC.
Yep. Hypertransport links. Yep.
So we will be tunneling over PCIe, effectively coherency protocols. Right now, the technology both behind PCIe and hypertransport in terms of differential pair is actually converging, and the reasons for us to run slightly different electricals is diminishing. We will always need PCIe, so trying to leverage that interface and use that going forward is definitely going to be our mandate, at least for a little while. And increasing that bandwidth, say using PCIe Gen 3 and other kinds of technologies going forward, is going to be a big avenue. I'm not saying we might not do coherent hypertransport, but we will definitely do PCIe with tunneling over it.
Terrific. Thanks, Eric. So we have time. I know we've gone a little long, but I'll do one more question from the audience, if there is one. Anybody else? Oh, OK. Eric, thank you. Sure. That was outstanding. Thanks for sharing that with us. We appreciate it.
Thank you very much.
OK, so there's our final keynote. Hopefully it delivered what we promoted to you yesterday, having our graphics CTO share next generation massively parallel GPU architectures that will find themselves in discrete GPUs sitting in HPC and data centers, in PCs, ultimately in APUs. Couple of additional comments as we close. Want to thank all of our keynote speakers, of course, Eric, Phil Rogers from AMD, Herb Sutter from Microsoft, Jim Davies from ARM, Graham Brown from Corel. I think they all really brought it and in their own way made an enormous contribution to our first Fusion 11, as did each of you. You guys really made this special. You were a big part of this. We want your feedback. We want you to help us to continue to improve and build on this event. So you can please participate in the survey material that you'll find for how to help us tweak this going forward. We do have a Fusion 11 Taipei event coming up in October. This has been our TFE event, for those of you who are familiar with it, where we literally have thousands of primarily Taiwanese engineers and members of the research community join. We're evolving that to be both a hardware and software developer conference. So that will be this October in Taipei. Look for more information on that. Want to again thank HP for all of the wonderful things that they brought to life next door in the Experience Zone. Also Accelaware. I dropped by the hands-on lab this morning. They said the traffic in there has just steadily increased throughout the week. A lot of people getting good hands-on experiences. That was a fantastic thing to hear. So thank you to both of them. And for your stomachs that might be getting a little hungry at this point, we have boxed lunches. You can stay here, enjoy them together, continue to network, or you can just take those with you if you choose and grab a quick bite on your way out. And with that, we'll close. So again, thank you. I think we've all been a part of a special start to the heterogeneous computing era. So thank you for that.